So moving on, we've just got here, obviously we've just done an acid carbonate reaction and I've just explained how to go through that. So then moving on, again, more properties with our lovely little acid here. So again, if we have a look at this structure here, just try and look here in regards to the functional groups. In this case here I have COOH. So what is this, guys? It's a carb acid, okay? It's a carboxylic acid. And here, what do I have here? Well, we can see the C, again, look at for the functional groups, that's CO, that's an ester. So it says name the product with the structure shown above, okay? So if I look here, it's an ester. All right, we name it from the side chain first, okay? In this case, that's ethyl. And there's my main chain, which has 1, 2, 3 carbons. So it's ethyl propanoate. Okay. It says state the conditions. State the conditions needed for this reaction. All right, we need to add plenty of H plus in there, and we need to heat it. All right, so generally the form of H plus is in the form of sulfuric acid, H2SO4, because it has 2 hydrogens. All right, so you get 2 hydrogens at a time. What else is probably the important thing to know about this here? That it's a catalyst, so we get it back at the end. All right. It said for the reaction, I've missed part C, I apologise. It says for the reaction involving another acid below, draw the structure of the other reactant. Well, again, we've got a carboxylic acid here going to an ester. What do we need in order for that to form? A carboxylic acid and an alcohol form the ester. And if you look at it, we already have the main part of, there's our carboxylic acid there, which is our carboxylic acid part here. All right, so what's left over? C2, CH3, but it's got to be an alcohol. So it's just going to look like this. CH3, CH2OH, which we all know to be ethanol. So again, it might look difficult to start with, but just look at what you're starting with and what you're finishing with and link them together, okay? It's either an alcohol or it's a carboxylic acid, it's an aldehyde, it's a ketone, it's an amine or an amide, okay? And just know where to split. So it's not hard, really, all right? You've just got to look for those certain tricks, look for functional groups and see where they repeat themselves. All right, part D. Naproxen is an over-the-counter aspirin alternative whose structure is shown below. All right, explain why this is not very soluble in water. All right, well, let's look at it. The big thing is it's a really big compound. All right, so it's a big compound. All right, and it's fairly non-polar. And it has large dispersion forces. Okay, so if I have a non-polar compound with large dispersion forces, it won't dissolve in water. All right, you might see this group here, your carboxylic acid group. Hey, wait a minute, this is polar here. Yes, it is, but the H bonding to just this part here will not account for the rest of the molecule, and therefore it won't dissolve. All right, so again, it's a big compound, and we would consider it to be non-polar. All right, or it's slightly polar, but it's not polar enough to dissolve in water. It has large dispersion forces. Okay, so if there are large dispersion forces, these molecules are going to want to stick together, and hence that's why they don't dissolve in water. All right, looking at this here, it says E, a wax commonly found on the leaves of plants, so the structural form is shown in the diagram below. Looking here, what do we see? Well, again, look for functional groups. I can see here, I can see a C with an O, which most people would think is a carbonyl group, which it is, but then they would say it's an ester. However, I can see another O up here as well, so there's my functional group there. It's a simple COO functional group. All right, so what will we call this? It's an ester. All right, explain whether you would expect this wax to readily decolorize a solution of bromine. Okay, would it? All right, in answer to this, you could say yes, because we have the double bond here. Okay, so it would to a certain extent, because you would get the addition reaction of bromine across there. However, very rarely do you get a compound that looks like C26, H53, C. All right, now remember you'll have an O out there with a C30, H61. You'll have a bromine off this one, you'll have oxygen and a bromine off that one. Doesn't necessarily occur because you've got these two big ones here. All right, so technically yes, it would decolorize, but in this case here it says readily, so my answer would be in this case no. All right, and the reason why I would say no is that even though we would get an addition reaction, the fact that this is very, very rare to get. All right. Then goes on to say, write the molecular formula of the carboxylic acid formed by the hydrolysis, okay, under acidic conditions of the wax. Okay, so again, let's look at this. I've got carboxylic acid, I've got hydrolysis, and if we look here, this was an ester group. So we've got C26H53. All right, that went to C with an O. And we know this is an ester from working it out before, so C30H61, C30H61. So we're going to hydrolyze it. It's a backwards reaction, okay, for an ester. Again, here is my ester functional group, which means that this here is the alcohol side chain, all right, and here is my main chain just here. All right, so my alcohol is my side chain, there's my carboxylic acid. All right, so alcohol would be C30H61OH, but my carboxylic acid would be C26H53COOH. Okay, it did ask to write the molecular structure, so you could have drawn it if you wanted to, but that would be your answer there. Okay. So again, question 4, here we go. All penicillins are based on the common unit, 6-amino-penicillianic acid. All right, the structural formula of 6-APA shown below. Again, what we've got to look at here are functional groups. So where do we see functional groups? We see one there. Okay, we see one here. We see one here. All right, so straight away I'm thinking amine there. All right, here I can see a C double bond to O, so we've got a carbonyl, but just check it first, what's it joined to, N. Now if that had a H off it, we'd call it an amide, but it's not. All right, and here I have a carboxylic acid. So it says here circle an amino group and state if it's primary, secondary or tertiary. Here's my amino group just here. It's worth 1 mark for circling it and 1 mark for stating the fact that it's primary. All right, why is it primary? Because my nitrogen is only attached to one other carbon. All right, draw the structural formula of 6-APA as it would exist at pH equal to 2. Let's have a look at this now. So what's going to happen here at pH equaling 2? We're going to get the Zwitter-on form. All right, we're going to keep adding H pluses. So if we add a H plus, what are we going to get? Well, that's an acid, so nothing's going to happen. These have nothing to do with acid bases, all right? The basic part of our property is our amine structure here, okay? And again, we should pick that up because they're asking about it in the part before. So use the part before to work out the next part. So all you would do there is draw that exact same structure, but you would draw a H plus off here as well. And that will give you what it would look like at pH of 2. All right? 3 they wanted to say draw, and why pH of 2? pH of 2 is highly acidic. So if it's highly acidic, it means we have lots of H pluses around the place, okay? So that's why we add the H plus there. All right, draw the structural form of the product that will result from the alkaline hydrolysis of the amide group in 6-APA. So even though this isn't quite right, the amide group is here, okay? And again, I'm not saying the amide group really needs a hydrogen attached off it in order to be classified as an amide group, but that's what they're looking for there. I don't think you'd get that in an exam. So to get the alkaline hydrolysis, you would have to break this, all right, and you would form alkaline being basic, all right. So you would get your base here, and you would get a salt there. All right, penicillin G can be made from 6-APA. The structural form of penicillin G is shown below. So it says draw the structural form of the chemical reactant used to form penicillin G from APA. So if we look back, all right, look back up here. it ends at the amine group, and we have the CH3s on this side. If I stop that here, so here's my amide. I have this here, which, if we look at it, is our 6-APA. So what is the chemical, first of all, again, if I look here, this part here, and I'll use a different color, this part here is a peptide, or not a peptide because it's not organic, this is an amide link. Alright, if that's an amide link, then this can break, can't it? Alright, to form an amine and a carboxylic acid. Well, here's your amine here, and here's your carb acid, and that would break through this middle point here. So changing back to blue, then my other structure would obviously be this benzene ring here, connected to the CH2, which then goes to my, and that's it, okay, because what's left over would be your 6-APA, which was given to you already. Again, they're trying to trick you by giving you an extremely large molecule, all right? But you've got to look at the functional groups. In this case here, it's our amide functional group. So look for those, look for ester functional groups, because they're going to want you to split them through hydrolysis, all right? Nothing else in this molecule has changed except for that one little functional group there. Alright, so name the type of reaction used to make penicillin 6 from 6-APA. So if I've got 6-APA, alright, and I put this lovely carboxylic acid, it's a condensation reaction. Alright, because we're making an amide, and we also get water produced from it as well. Alright, next one goes, the apparatus shown below is used to prepare the aldehyde butanol by the oxidation of an alcohol. Alright, it said the piece of labeled apparatus labeled A contains a mixture of the alcohol and sodium dichromate, which is up here, so you would expect that to be green at this point in time because it's not warmed. The pear-shaped flask contained labeled D contains 2 ml of sulfuric acid and 5 ml of water. Draw the structure of butanol. Well, again, butane being 4. This is really easy. 1, 2, 3, 4. All right, it's a aldehyde, so we make sure we get our bonds right. Again, you would be putting hydrogens on the end of these carbons, but because I'm going through it, we don't have to worry about it. Use the systematic name of the alcohol used to prepare butanol. Well, pretty easy, butanol. All right, would that get you the mark? No, all right, because butanol has at the end, all right, so it must be 1-butanol or butan-1-ol. All right, because if I had something like if I had butanol on the 2nd or 3rd carbon, we wouldn't get the aldehyde, would we? We would get the ketone. So make sure that you put your numbers in here in order to get your marks. All right. It says explain why butanol must be prepared using the apparatus as shown instead of refluxing the reactants. Now refluxing is where we don't worry about the Liebig condenser here. We have our flask, all right, and then we have our Liebig condenser up here. Water in this way, water out that way, and we just boil this here until the very end. However, the reason why I've got to take it halfway through is because we have a primary alcohol which goes to an aldehyde, which then goes to a carboxylic acid. So if I refluxed it, what would you expect to get? That's right, if I kept refluxing, I would go straight from my primary alcohol to my carboxylic acid and miss this aldehyde step altogether. So you have to put your Liebig condenser here in this distillation type setup, because you have to set it to a certain temperature so you know the aldehyde is coming off first before the carboxylic acid. All right. It says indicate on the diagram with the direction of water flow in and out. So again, here we have water coming in here and we have water coming out there, because we push the water uphill. All right, get it to defy gravity. Name the piece of apparatus labeled E. That's easy, it's a condenser. In actual fact, it's a Liebig condenser. I'm sure you would be fine if you just wrote condenser. All right, question 5. We might wait for the next video to go through there. I don't want this to go too long, so click on the next video.